All right, so here we have it. So the idea of today's talk, thank you so much. So the idea of today's talk was to talk a little bit about our experience with deep species distribution models. It's it's quite a new field for me as well, and I've been working on it for the last maybe 2-3 years. And I wanted just to give you a tour of the different things that we tried, things that worked, things that didn't, and so on and so forth. So since I'm the first to speak, I thought that a little bit of introduction will be interesting, even though these are unfortunately things that you all know, so that we are going straight to the wall in terms of biodiversity, and we're losing many, many species, and this is something that everybody in the room, I hope, is very concerned about and very excited to do something about it, especially because the loss of biodiversity is kind of a big wave coming. What did I do? I did something stupid now. Yeah. So it's kind of a big wave coming at us. Then it's up to you to decide whether climate change or biodiversity collapse is the bigger one. That's not the point. The point being that losing species makes us lose ecosystem services that are important for us as humanity and also for the planet in general. And I know I'm preaching an audience of convinced people, but in the end, the thing that we need to do, at least in my opinion, is to create means for efficient conservation so that we can inform and react to this type of threats. And one way to create this large-scale, consistent, and repetitive conservation is to map. Is to map all these different species that we have, and that's the idea of today, is to discuss ways to perform this mapping. And I guess that all the talks of the day will somehow gravitate around this topic of mapping species at the scale that you want to enable efficient conservation. Okay, so there are 3 parts in this talk. So this is the first. Every time you will be enjoying some generative AI figures trying to distill the idea of what is going on. And I wanted to start by talking about something that is not DeepSDM. This is a workshop about DeepSDM. And to talk about mapping with more traditional approaches, and then why this has brought us to expanding into DeepSDMs. So most of this part is based on this paper by Nina Fine-Thiel, who is a PhD candidate in my laboratory, and she did a absolutely stunningly wonderful job in this context. So it's the morning, and I'm pretty sure everybody is still craving for their 5th or 10th coffee. So let's try to have a little bit of a morning workout. So how many species of tree do you think there are on Earth? It's a workout for the brain. I'm not asking you to run. Contributions appreciated. You probably know, so you cannot play. Sorry? 70,000. Who says more? Who says less? 100,000. Who says more? Who says less? Come on, don't be shy. We're among friends. 10 million species. Seems like a lot. 50? Who says 50? You got trees. No. So you saw species in general. Yeah, no, in that case it's much more. We're talking about trees. And good first estimate, we have 73,000 species of trees, more or less, those that we know about. So, it's a lot, no? It's a lot of species. Let's continue. Where are these species?
Forests.
Good. I like that. I like the spirit. Rainforest? Not all of them. Come on.
On land.
On land. Good. On Earth, right? Good. Yeah, actually we don't really know. We know more or less. Now, you go to a museum, you see the distribution of species at the Jardin Botanique, whatever you want. You know more or less where they are, but we don't know exactly. But there are people who have been measuring that. Alexi knows a lot about it. So mapping, locating, and we have samples that tells us, oh, this species lives here. Okay, last question, which is probably the most interesting one, is where will they be, Emma? Do you have an idea? So if we knew where they are today, is it easy to know where they will be? Because that's the holy grail, right? Oh, this pointer is dying. On the moon, maybe. No, I mean, that's a kind of a rhetorical question. I mean, it depends. This is the answer. No, it depends on how climate is going to do. And these are the three questions. I mean, the second and the third. The first is answered. It's the question that we more or less try to address in this work. Okay, so but the core of this is that this allows me to give a micro introduction on what an SDM is. I mean, I guess more or less everybody in the room knows it, but basically we start with some geodata. In this case, we limited the samples to a polygon around the occurrences, and then we use all these geodata, which are climatic variables and things like that, soil variables, and we train some models. In this case, as I promised, no deep learning involved. Here we were talking about some random forest and some gradient boosting algorithms, which are very, very standard machine learning algorithms. And thanks to this, by sampling your climatic and soil variables everywhere on Earth, then you are able to learn a function that will tell you with a certain probability, is the species going to live here or not? At least it has the potential to live here or not, and it gives us what we call a species distribution map. Okay, and we had 26 million observations for 10,000 species. So you see, not 73,000, but because we had to use the species for which we had at least 90 samples, I think. So 90 records of where the species has been found. Okay, so that's more or less traditional SDMs. We could have used Maxent. We used the random forest. Fair enough. Okay. And it worked okay. I mean, it was an interesting study to run, and we were able to, having a 70-ish% of TSS. Also, that it goes down on independent validation because it's different areas, it's different species, and but the most important thing is that we were able to map these 10,000 species and to map them globally. So the fact that we use Google Earth Engine allowed a pretty easy pipeline to download the data, to organize it, and to run these models that are pretty basic, but they're also pretty implemented in Google Earth Engine. And thanks to these maps, then we were able to make different observations, such as the number of species, the range. We studied a number of interesting characteristics of the distribution of the species. It was not just, hey, here are the maps, let's move on to the next paper. But importantly, we also tried to tackle the third question, which was the where will they be question. Okay, so the idea was that we ran a number of climate models on different SSP, and that will correspond to potential evolution of the climate. And then we could have the distribution of the climatic variables in this period here, 2071, 2100. By having these maps of temperature, precipitation, humidity, then we reuse the random forest. Of course, we consider that there was no acclimation, but okay, I mean, that's the best we can do. And then we rerun our mapping, and we could then study what will happen in the distribution of the species given certain climatic scenarios. Okay, so what if we are in the 581 scenario, which is a little bit more harsh as a scenario where we do nothing. So in which biome we will have, for example, more species, that will be in boreal forest, for example, and in all the other biome, the number of species will decrease. The different species will try to go higher in altitude because of the increase of temperature, and also there will be important latitude shift mostly in temperate forests. So we could simulate, actually, the impact of future climate to a certain degree. I mean, there is it's not. This is also why we never disclosed the maps, because these are simulations, and then we didn't want someone to tell us, oh, but at this location it's impossible in this pixel. No. So the idea here is that we run a climate model, we get an idea of where the species might go, and then from there we aggregate our statistics and we give a hint on different climate scenarios of what will happen in terms of species. Okay, so how well am I doing time-wise? We started earlier. Yeah. Okay. No, because it seemed that. Good. Am I speaking too fast? Because that's something I do often. Okay, good. So then, so we have this first, experience in species distribution models, and then the project on DeepSDM came thanks to the Swiss National Science Foundation, and basically we started to explore deep species distribution models. And I mean, I'm not saying that at the beginning we knew exactly what we were doing. We probably didn't, but through cycles of disappointment and success, we are probably getting a little bit somewhere. And I wanted to show you now this middle step of looking around in different directions. But it all started by non-deep models. Again, it's just one slide, then we move to deep models, don't worry. And when we started looking at the literature, we found this paper by Valavi, which is very, very interesting because it's a comparison of many different machine learning models on this data set, which comprises species occurrences in different continents. So you have a map here if you want to locate yourself. And in this very nice radial plot, you can see all the models are the slices, let's say, and each part of the quadrant is a different location and species. Okay, so if you look at the radial plot without really obsessing on who is who, maybe one thing that you can see pretty well is that there is no clear winner, right? Most of the structures are vertical, meaning that in the end, all these models perform more or less the same. And we also try to reproduce this type of things, adding also some neural networks. And in the end, in this paper that we had in the climate change AI workshop at iClear, well, we realized that basically there is no clear winner, and all the models perform very, very similarly. So, I mean, this was the beginning of a project on deep learning for SDM, and the first thing we tried basically showed us that everything was more or less equivalent. So it was a bit of a depressive moment, and then we had to think a bit harder to why do we want to do that? I mean, what is the real advantage of deploying this technology of deep neural network, which is it's more complicated than a random forest. I think everybody in the room agrees to that, and so we tried to think about why this was relevant. Okay, so one first argument will be that using deep learning you catch all the nonlinear relationships. Okay, this is also true for random forest and to some extent to Maxent. So, but it's something that you didn't want to lose, the nonlinearity of the prediction, and check this was okay when using deep nets. But then, for me at least, the big advantages start to come when we think that this can be inherently multi-species. So we can have a single model that can predict thousands of species at once, something that, for example, Maxent cannot give you. And so this is also a very big speed up in term of calculations. And then at some point, it also opens door for trying to connect different species together in terms of all kind of community composition or species interaction, which you need a model that predicts multiple species at once for including this type of knowledge into your models. And also the species with little occurrences will enjoy the information coming from related species that have more occurrences. While if you have independent models, if you have a species with 3 occurrences, you're pretty sure you will model it pretty poorly. And then thirdly, moving into deep learning, in a way, releases you to this constraint of working with raster data all the time. I mean, no, with tabular data all the time, sorry. So you can start to work with raster data, we can start to work with text, we can start to work with sounds. I mean, you can really start to integrate different types of data as long as you can encode them into a vectorial form in a way or another. So for me, these were kind of very appealing properties that told me, okay, no, let's still do the project. Let's not give back the money. Because, of course, everybody will give back the money, right? Ooh, it's early. Thank you, Alexei. Alexei understands. Great. So we started working on that to the best of our knowledge. I come from remote sensing originally. That's my niche. And so we have been working on all kind of deep learning methods for remote sensing. And so we started to do something similar of what we were doing back in the day for satellite data. So we first thought, okay, all these predictors are collocated in space, but they are very different between each other. But at the same time, we can use them concurrently because they're collocated. So why not running some separate encoders? So there can be some ResNets here. It was the good old times of ResNet 50, and run them in parallel, get the features, 2,000 something dimensional, and then make them into a double-sized vector, so 4,096 dimensional vector, and use this vector. It was written, and then learn some kind of classifier that will classify all the species. I mean, that was one of the first things that we tried, and it took a little bit of tweaking and choosing optimal parameter and which fusion and this and that. But in the end, we got to something that was more or less reasonable, and then we started from there, and we started to tackle problems that were simply appearing as we went. One of the big ones was the fact that our labels are very often presence only. So we have observation of species, but when you don't have them, you don't know if the species is absent or if it was just nobody observed it, right? So we started to play tricks, and because machine learning people, we play tricks, and so we started to swap labels if they were in the same prediction unit. So if a species is observed very close, with a certain probability, swap the labels so that we try to counteract a little bit this presence-only problem. Robin Sminden had proposed a loss that take into account different types of pseudo-absences. And, by playing all these tricks, our model started to work better. Okay, at the beginning, it was a bit embarrassing, and, little by little, we got into something, let's say, reasonable. And, reasonable to a point where we were becoming reasonable also in terms of Joe Cliff. So that was Benjamin. He was very fond of Japan, so he always has his Japanese entry names. But yeah, so irrelevant. But this model here was the model with the label swap and everything, and we started to see that we were becoming competitive with respect to people who were doing that for a long time, and that was very reassuring to see that we were doing the right thing. And that was okay. Now, the third thing that we also played with was trying to understand scale in species distribution models. And maybe I wanted to spend a couple more slides on that. And the idea, that was also at the beginning of the project, is that we were always starting from the principle that a deep learning model is basically a computational machine. When you enter with a tensor, you learn some feature, and you exit with an answer. And most earlier models around were basically taking all the inputs, stacking them in a big tensor, and running whatever you want, VGG, ResNet, the latest fantasy from computer vision. But in the end, our predictors had very, very different meanings. So if we take the climatic variables, like here is the mean annual temperature over a good chunk of Europe, if you take a patch of a certain size, it will look like this. So it will be very, very smooth in some places. Maybe you don't see anything in your predictor. And sometimes it gets a lot of signal. But if you get a patch on a satellite image on the exact same place, you will see a detail that will correspond to a pixel here. So how can you put them in the same tensor and use them together in a deep learning model that will sum everything in the convolutions, and then you will just basically mix apples and potatoes. You say that in French? Yeah, pomme poire, apples and pears. Yeah. So we basically started like observing that, and then we thought, okay, let's study that a little bit consistently. So we started to build very simple neural networks that would, in a way, take that into account. Okay, so let's say we started with a model that was very simple. So we start with a type of variable. In this case, it's a bioclimatic one. Gets into some layers of a convolutional neural network. We get the features, and from those features, we choose one scale, so one spatial context, and finish extracting our values, and then having a linear layer that classifies. So basically, extract the image features, you focus on a single spatial scale, and you classify into your classes. In this case, we have some 3,000 classes. I'll come to that later. Okay, so that's the base model. It's a model that takes one input and pass it through a network, and we will get to an answer. Then we started to play around with scale. So we'll keep the same entry part, and then instead of having a single scale being extracted, we will extract 3 different scales, so the central pixel, a small context, and a larger context, and then an even larger context, and so on. And then having these 3 separate chunks of features and a linear layer combining them, we also retain interpretability in the sense that we can always track back which one of these 3 scales was the most important, because it's simply the coefficient of the linear layer. Diego knows very well what I'm talking about. That's a semantic bottleneck. And thirdly, since we don't have only the climatic variables, but we also have other types of variables, then we kept playing this, but with multiple sources of data. Okay, but each data remains at this native resolution, and we never compute them in a single tensor. We don't mix apples and pears and not potatoes. So in this case, here is the example with just one scale for the climate ones and 3 scales for the remote sensing ones. But this concept of scale is very, very modality specific, and will, in a way, tell you very different things. The scale at 25 pixels is by no means the same as the scale at 25 pixels in the other, because of the different resolution. Okay, so we work with GeoLife Clef 2023, so I thought to show examples with GeoLife Clef since we were in Montpellier. I wanted to be local a little bit. And so we have 2,000 and something plant species, and we trained on presence-only data, and we tested on presence-absence data. And this, I want to make that clear, because the numbers you will see later are very low. And this is because most people who participate in this contest, to max out performance, they train on presence-absence data. Because, of course, if you know where the absences are, everything is easier. But actually, out in the real world, we mostly have presence-only data. So we try to stay there. Again, for the predictors, we have the 19 bioclimatic variables at a very low resolution, and the Sentinel-2 at 10 meter. Okay, so this is what we got. So it's a lot of tables and graphics. Let me walk you through. I'll just go here so I see them better. And just don't look at you for a second, excuse me. Is there a screen? Yeah, but I cannot point there. It will not go there. Okay, so we have here a graphic for the bioclimatic variable. Here. Okay, this is dead. Good. So on the top left, you have the bioclimatic variables. So the thing that we observed is that the scale doesn't matter that much for the bioclimatic variables, which, in a way makes sense, because they are very, very smooth on average. So taking only the central pixel or taking a context around it doesn't really change a lot, apart from the computation time that will go from 1.5 hours to 10 hours. So, it's good to know. And also, when having multi-scale models, they also don't do a lot. But on satellite images, on the contrary, we see an improvement when using multiple scales. And this also makes sense, because you see different patterns at different scales. That's a very unique feature of satellite data, especially a reasonably high resolution like Sentinel. So using 3 scales concurrently leads to the best results. And even more importantly, let's see if it has rested enough. Yes, when you use both variable at the same time, so all the pink lines, it works better than using a single modality. And that's what you want, because otherwise what are we doing here? Doing GeoLife Clef with multiple sources of data or things like that, if using multiple sources of data doesn't improve the result. But fortunately, we have a 1.5, 2% improvement while using concurrently the climate and the remote sensing data. So they are both relevant, and if you use them together, you get this, this little push in performance. Of course, if you don't care about the extra 2%, you're probably better off with the bioclimatic data because they seem to perform a little bit better than the satellite ones. Which, also makes sense because it's some kind of direct measurements of the habitat. You have directly the temperature, the precipitation, and so on. While with the remote sensing data, in the end, you know if it's a tree or not, but all the rest is very indirect. So I'm ready to believe that the bioclimatic variables are more central than remote sensing ones for describing species distributions. Good. Are you still with me? Yeah, cool. Okay, so let's move to the third and last part of this talk, where I try to fill the last promise, which was to use multiple sources of data concurrently that are not forcedly, the usual raster. And this is I will present Mask SDM, which is our latest baby. I mean, it's still under review, but you can get it on archive if you are interested. And it's basically a modeling approach to be able to use multimodal data in an intelligent way for species distribution models. Let me walk you through. So here, as I told you before, we started from the idea that we have many of these sources of data, each one characterized by several variables as well. So when we model species, we want to know about different things, right? We want to know about the temperature, the precipitation, the soils, topography, location. I mean, there are so many things that make what makes a location suitable or not for a species. And very often we are, we don't have them all. We are forced to omit one or another. But I mean, we always try to use all those that we have at hand. And now, since some time, since a few years, we also, we start to work on remote sensing, so rasters with a spatial component. There is the time dimensions because satellites keep to record, so we have time series. Let them be climatic or satellite-based. And then we also have raster of climatic data, and then you name them, and there is text, there are reports, there is eDNA, sound. I mean, you could imagine using all of this at the same time. But they are of very different nature, right? They are quite heterogeneous. It's difficult to find an approach that can just take them all, put them in a single tensor, and run them into a ResNet, no? Which is what we have been doing a lot. So we thought about a way to make this possible, and then tested it with some data that we had at hand. Okay, given that, the question that we asked ourselves was, if it was possible to use all this data, even though they are very different, I mean, what is it that we would like to obtain from the model? So I'll say that well. Which capabilities you want the model to have? What would you like to have? If I told you, hey, I have a model that can ingest whatever you want, what do you want this model to be able to do?
We still like the model to tell us for which species, which type of variable matters.
Fantastic. Very good. Very good. Yes?
More robust.
More robust. Did you see the slides? No. Okay, robust in which sense?
More transferable.
Mm-hmm. Okay. One more? Come on, give me the third one I want to talk about, and then I will be very happy.
Maybe more interpretable.
Oh my God. So, I didn't talk with these three people. I didn't pay them in advance. But The first thing that we want is robustness. So if you don't have one of the feature, can I still run the model? Or does it work well in another place? Which is the same. Second, can we know which variable is important for which species? So having the flexibility to analyze what the model is doing. And third, explainability. So given a result, can I trace back what happened? This was fantastic. Thank you very much. Thank you, thank you, thank you. A little bit of an applause for our... I'm impressed. I'm very, very impressed. Cool. So this is what our mask SDM pretends to be doing, and I think it does it in a decent way. Okay, good. So we started from what was around, and we thought, okay, what do traditional approaches do when a modality is missing? What do? You move the carpet and you put the variable under the carpet. This variable doesn't exist because I don't have it in that part of my data set. Or if you miss just some records, you can do imputation. No? You say, okay, I don't have the value here for X reasons. Let's take the average of the 10 closest one. Huh? Or let's take the average of the one before and the one after, if it's time. And usually, you get away with it. We thought of working a little bit different and to include the fact of some variables or records will be missing directly in the learning process. And so we decided to introduce a learning objective that it's really based on the fact that sometimes you have them and sometimes you don't. Okay, this comes from NLP, if you know a model like BERT. It's called masked language modeling in NLP because they work with language. And it's basically very simple, actually. You have a model here that is taking words and try to predict, to reconstruct the word or predict the next. I mean, it depends on the task. And basically what you do is that every now and then, you will just mask the word. So, I don't know what the input is, and you'll try to predict the next. Or you try to predict itself from what has been observed before and after. And since this model in the middle is what we call a transformer, I don't know if you're familiar with it, the transformer is a model that is specialized on sequences of data, and not only specialized on sequences, but it just connects every position in the sentence to all the others. So basically, you can predict what this word is because you know that before it you have how are, and after you have doing today, so it's probably you, the word that you are looking for. And that's something we all do. I mean, given some context, it's easier to predict something that is missing. Fair enough. So we applied something similar in mask SDM, and basically, I mean, something very, very similar, and a training time here. So we have all our data of training. For this specific sample, we had the satellite data, we didn't have the topography, we had the climatic information, we didn't have a positional encoding. I mean, how can you not have a positional encoding? Fair enough. And basically, but when the input is not available, you replace the feature that should be there by a mask token. So you basically tell the model, I don't have this information. And then you even pass all these guys through a probability threshold where some of them will be masked even if you have them. Okay? And then basically the job of the model is to predict the distribution by having only partial information. And since you do it a million, gazillion, a billion times, basically the model starts to learn how to predict even when these masked tokens are in. Exactly the same way as the language model does. Okay? By using context. So if I have this feature and this feature should be more or less this. Okay? So we don't do exactly masked language learning because we don't try to reconstruct the feature at the input, but we simply try to predict the species and then have some gradient flowing back and learning all the different features. So every colored little line here is a feature extracted from one different type of data. And at inference, so when you go on prediction this time, you see that all the models are frozen this time, you just do inference. And when you don't have an input, well, you just replace this feature by the masked token. And since at learning, the model has learned to predict with only partial information, it basically doesn't care. It will take the features that you have, and for the others, it will just ignore them and make the prediction in absence of the different input tokens. And this is it, my friends, because basically it's a model that allows you to learn in presence or absence of different modalities, as long as you have at least one. I mean, if you don't have one, then what are we doing here? Huh? Okay, let me show you a couple of results. So this time we're working on splot. Sorry, no Joe Life Cliff this time. But so we have different plots that have been analyzed specifically. So it's very sparse, spatially. As you can see, it's also America and Europe centric. But okay, we have 10,000 species that have been observed in these 90,000 plots, and our data are this times presence absence. So it's a very curated data set, but you know, we wanted to have some data that were, you know, well documented and learn the best way that we can. So for now we're not looking at presence only, but we wanted to be sure that if we were predicting a species, it was actually there. Okay, we used a bunch of predictors. It is completely useless to look at the exact list. Just I wanted to show you that we have more or less all the categories going from climate to soil, topography, location, human influence, so presence on road and so on. Some metadata that you can find. And finally, something related to satellite images. We didn't take the satellite images themselves, but we used the embeddings from SatClip, which is a method proposed by Konstantin Klemmer last Triple AI, where they basically have an encoding of all location in the world. So instead of downloading the satellite images, you download the embeddings and you download a vector instead of downloading a full remote sensing images with multiple bands. So it's much less data to be downloaded, basically. And it should be the same, should. Okay, good. So first question, I mean, does MaskSDM work as we wanted? So we have here 3 blocks of approaches. I will walk you through them, and then we will talk about how this works. Let's start from the bottom, obviously. So the oracle here is a model trained specifically on the features that you are here at the top. Okay? So we have 9 cases here. It means that these are 9 separate models optimized exactly for this feature set. So it's a little bit, it's the model to reach. Now it's an upper bound. Then all the other models here are a single model that is trained on what's available. When it's available, you use it. When it's not available, you don't use it. The main difference is how you deal with this missing data. So we have MaskSDM, and you know exactly what it is. And then you have the usual suspects of imputation methods. So you try to replace missing values by some average in a certain region, and so on. So the good news is that MaskSDM works very well. So you know it's almost always reaching the upper bound. As all the models, when you are using only the average temperature to predict 10,000 species, it doesn't work so well. But we're still close to the oracle, and even the oracle goes worsely in that case, so that's okay. The interesting thing to observe here is that the imputation methods degrade very, very quickly when you have less and less data, because of course there is more data to impute, and needing more data to impute makes that your prediction will forcibly become less accurate. But MaskSDM, fortunately, since it learns all these relations concurrently with the masked modeling and the transformer, manages basically to learn even when at inference time you have only the the average temperature, and the work lim variables. So I think this is quite powerful to see that in the end, even with very little information, the model is capable to making good predictions. So flexibility. Yes, you go to a place where you don't have a variable, you can still run inference, and it still works, more or less, at the same time, level of accuracy. Then, again, we have a single model that encompasses all the modalities, but if you remember, at inference time, you can turn it on and off. If I just go back to, just that you remember, when the model is trained, at inference, you can just decide not to input one modality, and it should still work, right? This also allows you to very, very quickly assess whether a variable is important or not. You just run inference without that variables, and you see the difference in performance. And this is what you see here. Oop. So all these numbers are obtained with the same model, just having inference pass, removing or not certain variables. And in the end, we can then assess the importance of the environmental variables, of course. And the more types of variables, the better it gets. And then you can also look inside the environmental variables and see how the single sub-variables have an influence on the final results. And this is done just by inference pass, so it takes minutes and not the hours it will take to train a single model just with this, just with this, just with that. Okay? So also for evaluating the model, it has some good properties. Now, this also applies to the mapping, right? So we are now able to map the species distribution of, in this case, the Antilles vulneraria with different inputs by using the same model and just masking the inputs. And so it's a single, all these maps come from the same model. You just turn on and off different variables, and then you can have the accuracy of your mapping. So you can have single species maps just at inference time by playing this trick of turning them on and off, and you can have per species assessments and the specialized maps at basically no additional cost. And again, if you want to compare to the Oracle, so this is the Oracle, so it's a model that has been trained specifically to each combination of inputs. I'm sorry, it's very small. So we have here the average temperature, the work limb climate variables, then work limb plus soil grids, and this is work limb, soil grids, topography, and location. And then you see, of course, the maps get better and better the more inputs you put. But these 4 maps are made by different models, trained in a different way, each one taking the time it takes to train them. This is a single pass, just turning the models on and off. And this is the version when you just impute the missing values, and you can see that it's not fantastic. All right, how am I doing? Yes. I'm doing okay, time-wise. So let me conclude. I hope it was a good start of the day, and it was interesting. So let's say bye to Bugs Bunny. And so after roughly 3 years working on DeepSDM, well, I'm still convinced that it's a good thing to keep working on. God bless. And it's an approach that allows us to work on multiple species at the same time, to still map at scale, even though, I mean, you could think this computationally very expensive, but actually, depending on the choices you made, you can get away from it with reasonable computation and approaches that need a single model for having multiple input-output combinations are probably the way to go. And then finally, I mean, there is still a lot to do. So we are not considering all the data that we have at hand, and this is something I would like to work a little bit deeper in. I've never worked with those eDNA data or the sound, text. I have a little bit of experience from my remote sensing hat, but haven't really worked on text here. So trying to put all these different data sources together is definitely something I will be interested in. And then, I mean, we've talked a lot about data, but there is also a lot of things that we know about how the species interact between each other, how they predate, how they co-inhabit space, and this, for the moment, is completely ignored by these models. These models take some data, predict some distribution, but if species A eats species B, that's something that the model completely ignores. So why not including some biology into those models? I think that would be a great thing to do. Anyway, so before stopping, I wanted to thank the people who have been, doing most of the heavy lifting. I'm just the messenger, and the guy who is here telling you nice stories and making you laugh. But these guys are actually the people who did all the modeling and the heavy lifting. They're great, and some of them are even in the room. And that's it. Thank you very much. If you have questions, here I am.
Any question? Don't be shy. Flora?
Yeah, thanks. I wanted to ask one question about the mask SDM. When you're masking, traditionally in SDM modeling, people are very concerned about collinearity. So you have two variables that essentially have a very similar signal, and about the ability of the model to identify which is really the causal variable. When you're masking and you have this large number of variables that maybe all have very similar signals, aren't you just forcing the model to partly explain the signal with the different variables? So I'm wondering, have you made any tests whether it's able, when masking, whether it's able to identify the right causal variable, which might of course be a concern for extrapolation?
No, it's an excellent point, and it's also something that I hear a lot in my remote sensing job, which is people want to know which are the relevant bands. And then when you have an hyperspectral sensor with 200 bands, they want to know if it's 155 or 156, while there are 10 nanometers apart, and they basically tell you the same thing. So yeah, I mean, that's definitely one thing that might happen. I think that it's a practical solution to be able to deal with missing variables by exploiting the correlation between variables. Then in the training that we do here, we mask entire modalities rather than single variable within the modalities. But in the inference passes, when we do explainability, we mask entries of single variables to assess the explainability of every single variable. And in that case, we enter in this case that you described. But again, I think that averaging that out, having the importance of a single variable still emerges, even though for one specific record you mask one for another. And then overall, I think overall you get to the same results, right? I think that this is a good engineering tricks to be able to overcome this type of missing variables. No?
Yeah, we've also played around with this, I think, for prediction, for sure. Yeah. But for the question is, aren't you kind of forcing the model to get redundant, which is good for prediction, but problematic for inference? That's my concern. For inference, so for inference in the sense of statistical inference, if you want to have the interpretability. If you want to make sure that, let's say, the effect comes from temperature, not from the satellite signal, which can substitute for temperature again. Mm-hmm.
Yeah, but at the same time, what you want is to have the right map, no?
Yeah. With that, I agree. But with the interpretability, again, okay, but I think...
Yeah.
I had a similar question, but maybe a way to reformulate it is, if you change the distribution of the masks, the random distribution, does it change the interpretability? I mean, if you, for instance, instead of randomly masking each modality, if you had some more complex way of masking, like I always mask those two modalities, it's an extreme case, then you will change the interpretability in the end. So, yeah.
Yeah, at the same time, this will be forcing the model to have an incorrect behavior, right?
Yeah. But yeah, that's, yeah. Okay. Please.
Well, I only have a comment to this. Isn't this an issue of having two different goals? So you either have a model that's meant to predict well, or another that's used for interpretation. So if you want your model to be good in interpretation, then you would focus on having reduced collinearity, specific variables. But if your model is really good at predicting, I don't think you really care which variable is selected.
Yeah, I think that there is part of that in the answer, that this model is mostly aiming at predicting. And then for the interpretability, we always try to summarize that on a whole data set level, more than looking at a specific species, specific location, to avoid this type of effects.
Yeah, and then again, when the model is going to be good in interpretability, it might not really be good in prediction. So it's gonna be easier to understand for us, but when it performs specifically for prediction, it's gonna be outperformed by a model that's very precise, but maybe uses some variables that we don't really understand.
Yeah.
Well, that's just a comment, sorry.
Thank you.
Thank you. Other question?
I think there was a question from the back.
Thank you. Perhaps I missed some points, but I wonder how do you take into account uncertainties. I think it's
Sorry, can you speak in the microphone?
Okay.
Yeah.
I think it's related to the discussions, previous discussions, but how do you take into account uncertainties? How do you quantify uncertainties of the probability of the prediction? And another thing is that there is very classical approach for species distribution model to use, for instance, random forest or something like this. That you compare it, and how do you avoid the problem of clustering, sampling, or do you take into account spatial variations between predictors and observations? Exactly what we have we have this kind of problem with usual statistical model, and how do you correct all these kind of things?
Okay, so for the second, we sample spatially semi-uniformly, and we reserve some areas for test and validation to avoid spatial autocorrelation, and we also make these blocks very big to avoid the spatial tensor to overlap each other. And then we have no control on the spatial distribution of the points because they come from data sets. So we didn't sample them ourselves. Now we have this sampling that is mostly driven by space. That's the way we do it. And the first question was, sorry?
Uncertainties.
The uncertainties. So to quantify uncertainties here, we basically run the inference multiple times. Yeah. You don't seem happy with the answer. I mean, we have been running student projects over and over, comparing Bayesian networks and test time augmentation and whatever you want. In the end, it's always the same. So why not going for the simplest solution? It's Occam's razor in the end, no?
So thank you. I think, yeah, maybe some of the questions will be also meaningful for other speakers, so that's why we can also move on. But yeah, very quickly.
Like a very quick comment, going back to the previous question of Florian, just to discuss, maybe not to answer now, but just to discuss, because it's, so for the collinearity problem, like if you have two variables that are perfectly collinear, one has like a causal relationship directly with the prediction, the other one doesn't, but we don't know anything about the causal structure, right, of the problem a priori. This is a predictive problem. Wouldn't actually you want in that case that both are given the same importance, since you don't really know anything about the causal structure? Like isn't a model that is forced to choose one or the other arbitrarily more problematic than one that is said, okay, if the two are collinear, both are given exactly the same importance? So it's just like a question of whether, like, which of the two properties is more desirable.
I think it's asking to you, Florian. Because he's looking at you when he's talking.
I will say I have a few slides on my talk, then we can discuss it later.
Fair enough, fair enough.
So that's a fantastic transition. And so thanks again, Devis.